Welcome to Steady State Two-Dimensional Temperature Gradients with Nodal Analysis by Trever Plastow and Mike Hare. Differential elements can be derived from three-dimensional shapes, and energy balances can be applied to be able to create temperature gradient throughout the object, which will, when used, help you identify what the temperature is at individual points. The problem is, we don't have a way to be able to do that mathematically, so we need to do it numerically. We begin by separating the object into a simplified form, in this case, a cylinder. The cylinder is given basic coordinates. We take z and r, for example. Nodal analysis is exactly that. Nodes being analyzed and meshed together to compare one against another. So we begin by separating the object into a whole bunch of different nodes. We create a basic coordinate system and refer to each object. Now, when we go and we look at it, we can take one single node, for example, the center of this yellow circle. And we can expand that circle out, and we have basically the change in R and the change in Z as the little tiny spaces on the nodes. And as we go and we compare one node to the nodes around it, they end up becoming A minus 1, comma B as one location, or A comma B plus 1 as one space away from the location of A comma B. Now the temperature at one location right next to an object, the temperature at the other location, one space to the other side of it, will help you find out what the temperature is approximately of the point that you're identifying. For example, A is pretty much the same thing as A plus 1 and A minus 1 divided by 2. It's about the average. So, by simplifying the infinite difference form of the heat equation, and if delta R equals delta Z, meaning the steps that you go up and down and left and right are the same, an approximate algebraic equation is given as seen. This is only applicable for an interior node. If the nodes are not existent next to it, you have to apply boundary conditions. These boundary conditions come from the initial energy balance, but it simplified down to this one, for example, where you have an exterior node facing external convection. We basically had to separate out each and every location, so the corners, the four corners, were individual nodes. And then each one of the sides had their own equations because of the type of node that they were and the boundary condition that was applicable.
Plugging these 9 different boundary conditions into our numerical methods program, we can now determine the temperature of any point if we know the temperature at the surrounding edges. For example, in this picture as shown, we would have a convection boundary condition of 20 degrees Celsius, 2 different surface temperatures on the top and the bottom, and an insulated assumption at the center line of our cylinder. If we were to rotate this around, we would see that the temperatures would be constant at the same radial and z coordinate. For our first test, we used an aluminum cylinder, which we had drilled holes at different depths and heights in order to measure the temperatures at different r and z coordinates. We quickly found out that as the hot plate heated up the aluminum cylinder, it would quickly sink into the ice block, thus changing the boundary conditions. Condensation also formed on the outside of the cylinder, which changed the heat due to convection. For our second test, we decided to use 2 hot plates instead of the ice block in order to eliminate some of these difficulties. We got a better temperature gradient throughout. However, our measured results were still a lot different than what we had anticipated, as the hot plates had a duty cycle in order to keep the temperature at a constant rate. Using our numerical methods, we determined that the more iterations you use will yield better results than using a smaller step size. For example, with the same boundary conditions, if we use a step size of 1/4 millimeter, with only 100 iterations versus a step size of 4 millimeters and 10,000 iterations, we can see that the larger iterations, even though using a larger step size, will give us a better clue of what the overall trend is. Using Nusselt correlations, we calculated an H value of 32 for the test situation with 2 hot plates. This seems a little high for free convection. However, when we change the H value in our numerical method to something much lower, you can see that there really wasn't much of an effect. In conclusion, we were able to find an answer to this incredibly complex differential equation by using simple algebra 55 million times. We're very confident in our analytical solution, even though our experimental results were unconclusive. If we were to do the experimental test again, we would do something along the lines of the second test, using 2 hot plates. We would need to make sure that the top and bottom surfaces of the cylinder are at constant temperatures, as the hot plates used a duty cycle to turn on and off in order to achieve a certain average temperature. A constant surface temperature on the cylinder would yield more accurate results. Thank you.